Good afternoon, everyone, and welcome to this webinar. My name is Vijay Kutcherkar, and today we're going to take a look at how you can solve some injection molding problems using 3D simulation. The first problem that we're going to look at was observed on a medical tray. Okay, so a company was trying to make this medical tray out of polycarbonate, and they had some experience making parts like this. They did not use any kind of simulation at the time. So based on their experience, they felt that they should go with a gate location here. And they found some information online and through some literature and from their material supplier for gate dimensions, some recommendations for the gate dimension. So they went with that and their experience. And they set this up, they built the tool, and they ran the trial. Now, the first part that they got from their trial looked like this. So as you can see, calling this part unacceptable is a bit of an understatement. It's a pretty bad part. Now, when something like this comes out of the tool, and hopefully your customer is not there with you when this happens, but when this comes out of the tool, you really don't know what caused this. Someone will blame the part design, someone will blame the tool design, someone will blame the molding machine, others may blame the material. So it's really hard to understand what happened inside the tool, what caused this problem. And this is a place where simulation can help you quite a bit, especially 3D simulation. So what I'm showing here now is a result that we get from a 3D simulation. It's known as packing melting core. This result tells us what is still molten and what has solidified in the part during the molding cycle. So anything that you see in blue is still molten, and whatever has become transparent has solidified. So I'm going to play the video which shows you essentially how the part cools from when the packing timer starts to when the cooling timer ends. So here you can see everything is molten and then it starts solidifying, and then you get almost everything is solid. Because this is a thick part, you actually do have some regions that are still molten at the end of cooling. That's within the thickness. So let me play that again. Now what's interesting here, I'm going to pause it. This is all molten, so which means all this molten polymer here is still connected to the molding machine. So all this is still receiving packing pressure. Watch what happens now. So here we're getting to this point where all this is solidifying. You have all this molten region in the back. As we go further down the cycle, you can see here that now this section has lost connection with the sprue and the molding machine, which means that this section here is not receiving packing pressure anymore. And because it's not receiving packing pressure anymore, it's cooling in the absence of packing pressure, so it's going to shrink differently. And warpage is nothing but differential shrinkage, different parts shrinking differently. And this is really what caused the problem that they observed from their first molding trial. Now that you've run the analysis and you've understood why, what's causing the problem, you can start thinking about the solution and take a more direct approach to the solution. So here's again, you can see the connection here is lost. The back of the part does not receive any packing pressure. So now that we understood the problem, the solution becomes quite obvious. We have to do something to ensure that the back of the part continues to receive packing pressure. Before running the analysis, someone may have suggested, let's increase the gate size. By increasing the gate size, it would take longer for the gate to solidify, of course, but that wouldn't solve the problem that we saw where this section here is solidifying and it loses connection to the injection molding machine. So really, to solve this problem, it would be best to add another gate so that even if you lose the connection here, the back of the part continues to pack out, the gate continues to pack out the back of the part. So let's see the results from that setup. Here I've paused it at this point where you can see now that this gate has lost connection with the rest of the part, but this gate is still connected. So the part does receive a better distribution of packing pressure. Let me play that again. You can see here the connection is lost, but the back of the part for some time continues to pack out the rest of the part. So they went ahead with this design. Okay, you can see here again is an image showing the connection is still there. The rest of the part is receiving packing pressure. And now this is the part they got when they ran with the optimized design. You can see it's much better. Here's a before after, here's the unacceptable part, and here's the acceptable part. So here you saw how 3D simulation helped us understand the problem, but also helped us get to the solution a lot quicker. Because again, someone may have suggested, let's change the cooling channel design. Someone may have suggested, let's optimize the processing conditions or increase the gate geometry. But once we ran the analysis, we understood where the problem came from and helped us get to the solution a lot quicker. The next case study has to do with viscous heating. Now, even if you have a perfectly symmetric runner system and you have a perfectly designed cooling system, you may still see imbalance between your parts. So when you have a runner system like this, you may see that some cavities are filling faster than others, and then even within the cavity, you may see that one side of the part fills faster than the other. Now, let's first understand why this happens. When the material comes in through this runner, it's rubbing against the steel wall here, where you have most of the shear effects. The shear stress is higher close to the walls, and then it gets minimum down to the center of the channel. So it's picking up heat as it's flowing through this channel. When you get to this intersection, the hot material wants to travel down a certain path, and the cold material wants to travel down this path. Here you'll see that the hot material actually prefers to go down this path, which is why you see this side of the part filling faster than the other. Now, there's two questions here. Does this happen every time? And the answer is not really. Whether this happens or not depends on the viscosity of the material, it depends on the injection velocity, and it depends on the size of the runner system. So you have to have a perfect storm of these conditions to get significant viscous heating that will give you this problem. So by using 3D simulation, you can first check your design whether this is going to happen. This is something you need to worry about. And then, of course, if it's something you have to worry about, then simulation can help you find the solution to the problem. Now, simulating this is not easy. You definitely need to run a 3D analysis. You cannot get these results from a 1D analysis of the runner system. You need to have 3D analysis. Now, even when you're doing 3D analysis, you need to make sure that you have high resolution mesh. You have a high number of elements through the runner channels to capture this effect. There's a few options of the different mesh types that you can use. If you tried using a pure tetra or a pure brick or a voxel mesh, you would have to use an extremely high element count, which would result in very high simulation times. The first time I tried to do this in 2006, I used a pure brick, a voxel mesh, and the computer pretty much ran for 2 or 3 days before I got a result. And then even then, I was in R&D, so that was a different story. If in the real world, you don't have that much time to run a simulation. The better approach is to use a boundary layer mesh, where you put prism elements near the wall where the shear stress is the highest, and then through the thickness you use tetra elements. This way you get the higher resolution that you need, and you significantly lower the element count for this. This enables you to get these results in a matter of hours as opposed to several hours or days. Where you can capture this viscous heating. Sometimes, depending on the system, you could get your results in less than an hour. Now, even there, when you're trying to use boundary layer mesh, in the past, at any junction, you would have to use tetra meshes, where you have a very high element count. Now with some new developments, these junctions are meshed much better. So you have a much more ordered structure in here. So whereas in the past, if you needed 60,000 elements, you can now reduce that by more than half to capture viscous heating in practical times. So now that you have the ability to simulate it, you can take your geometry. Now this was a case where they're trying to make this round part and they're feeding it with 3 gates. Now you would expect, if you just looked at it, you would expect maybe this leg would fill faster than this leg. Because all the dimensions are the same, identical, I hope that everything fills uniformly. But if anything, you would expect this one to fill faster. In reality, quite the opposite happened. When you run the simulation, and also from what they observed, they saw that this runner was the slowest to fill. You had a preferential flow down these 2 runners. So when we run the 3D simulation, now you can see why. The hot material, when it comes to this junction, prefers to flow this way, and then the colder material that's in the middle goes down this way, which is why you get differential or imbalanced filling on these parts. So here you can see a comparison between the filling pattern, right? You can see that these sides are filling much slower. This one is filling faster. Okay, this gate here is fed by the C channel, so these 2 sides fill faster than what is being fed by the C runner. Okay. Now that you're able to simulate this and capture the problem, now you can start thinking about solutions on how to solve this problem. So you could end up with something like a melt flipper or a mixer in there to try to distribute the temperature a little bit better. Or you could try to make your runners bigger, because again, the problem is happening because of viscous heating. If you make the runners bigger or go with a lower viscosity material, or if you slow down your injection velocity, you may be able to solve this problem without really adding any sort of a device in there. But once you have the ability to simulate it, you can then figure out the best solution for your project. The next case study has to do with visual defects. Now, this is a case of an automotive part. You see this is a 2-cavity mold that is fed by 4 drops. Now, sequential molding has been around for a long time. To avoid well lines, people will time the opening of these drops to control the flow fronts to avoid well lines and get the filling pattern that they require. Simulating this has also been around for a while. We've been able to simulate sequential molding. But when we're doing so, we assume that the gate is either closed or fully open. And you cannot really simulate, you could not really simulate opening and closing of the valve gate. Okay. So now what happens, because now software has been developed, technology has been developed where you can simulate opening and closing of these valve gates, and you can control the velocity of how fast these gates open and close, which is why now you can predict this sort of a hesitation when that gate opens. So watch this. While the material is moving down, this gate opens, and you can see this hesitation there. In the past, you would not see this hesitation because the gate would either be open or fully closed. And if you're doing a 3D analysis, you would have to model the runner system in the fully open position, so you wouldn't really see this effect. And then you would observe problems in the part, such as this. You have these appearance issues due to the hesitation that's created. Now, to solve the problem, again, because now in simulation we can simulate opening and closing of the valve pin, and this was quite hard to do because you have to, the developers actually have to adjust the mesh while the simulation is running. So this was not easy to do, but now that you have the ability to do it, you can see how you can control the opening and closing of the pin. So the original analysis was at about 6.3 seconds, you fully open the valve pin and it goes to its fully open position. In the optimized design, you start opening the valve pin at a slow velocity up to 8 seconds, and then once the valve pin has gone up a little bit, you then open it to its fully open position. Now here you can see a much more controlled flow front. You don't have that hesitation effect because you profiled the opening of this valve pin. And now here you can see the before after pictures for this. Here you can see the hesitation lines. Here you can see they've gone away. Again, here you can see the hesitation. Here you can see that it's gone away. So this is a combination of technology that allows you to, first of all, be able to open and close the valve pin and control that opening and closing of the valve pin. And then you now also have the ability to simulate it to catch the problem before it happens. Okay. Now I'd like to talk about a metal replacement project. So this is something that's quite common in especially the aerospace industry and automotive industry, where people are replacing metal parts with plastic parts. And they tend to be, the part designs tend to be much thicker than what's recommended in plastic part design. So this customer, after they molded the part and they scanned it, they noticed a lot of voids in their part. So let me play the video of their scan. It's loading up in a moment. Now here you can see, let me try to pause it right where you see the void. So here's one void up here. Okay, here you can see more voids in this section. Here you can see some more voids here. So they had voids essentially all over their part, right? So that's when they decided to, let's run a simulation to figure out the problem. So they ran an analysis on their complex part with many different wall thicknesses, as you can see. They started there originally, they had a 7mm cold runner. Looking at that same melt core result at about 13 seconds, you can see that all this is still molten, but it's lost connection to the sprue. So it's not receiving packing pressure anymore. So to solve the problem, in this case, they said, let's see what happens if we increase the cold runner diameter so that the gate doesn't freeze off quickly. You have a larger runner. And they added some flow leaders into the part to distribute the material differently. Now, at even 18 seconds, you can see that the connection is still there, and most of the part that was molten received the packing pressure, and even at 18 seconds, the connection still exists. So this part packs much better than the previous version. So here you can see this was at 13 seconds, this was at 18 seconds, and the connection is still there between the machine and all this molten polymer. So now when they scan this new part, as you will see, let me play the video. You can see now all those voids went away once they went with the part modification as well as the new runner system. Okay. Now this project was using conformal cooling, and the customer wanted to reduce his cycle time. So we asked them to send us the original model of what they were running. They did not like the cycle time they had there, so we looked at the cooling system. And here you can see they used a traditional cooling system by drilling channels in everywhere. Now, based on the part design, you can see because this part is curved over here, you can see that this section of the part is far away from this cooling channel. There was no cooling in here at all, right? So even before running an analysis, once you've done this for a while, you can expect problems from this cooling channel design. And as expected, after running the analysis, you can see here that this section is very hot, and this section is also hotter than the rest of the part. So the additional cycle time that's being consumed is to cool this section, right? So if we can do something to reduce, to make this temperature more uniform, and so that everything cools more uniformly, you should be able to reduce the cycle time significantly. So what they did is they designed conformal cooling channels. Now they took advantage of the new technology out there to come up with really nice cooling channels that conform to the shape of the part. So they had cooling channels like this to conform to the inner side. They had cooling channels out here to better follow the profile. And of course, they made sure that they had a cooling channel in there. And then they ran an analysis on it, again, before cutting the steel to see how much of an effect it has. So here you can see that now at the end of cooling, or everything has cooled. And here you can see the before after picture of temperature. This resulted in a 69% reduction in cycle time for them. So that's huge when you're trying to reduce cycle time. Okay. The final case study I'd like to present today had to do with reducing warpage on a part. This customer tried to make a part and they had to assemble two pieces together, and their specification for this gap here was 0.3 millimeters. And what they ended up with after they made the parts, they had a gap of 2.3 millimeters. So of course, that's not acceptable. Now, after running the simulation, you can compare the warpage with your target. So you can extract a curve from your CAD model, and then you can compare it with the warpage on that surface. And here you can see the warpage was close to what they observed on during the molding trials. So it's, again, you can see it's unacceptable. They also observed that their pressure drop was too high. And they, after looking at the temperature results, they noticed that this section had a hot area. So basically, where the way the cooling channels were designed, they were not close to this region, so this ended up being hot. Now, warpage is a factor of many things. It could be due to the part design, it could be due to the temperature distribution, or it could be due to the pressure distribution, and it, of course, could be a combination of all of the above. So to really study what influences the warpage of their part, they did the analysis and they said, okay, let's try to fix a few things. So to improve the thermal factors, they came up with design A, where they added some cooling channels. Design B and C were to deal with the part design, so they added more ribs, they changed the gate locations, they increased the wall section by 0.3 millimeters. Then to counter pressure drop issues, they reduced the length of the runner system, and they said, let's see what happens when we go from cold runner to a hot runner. So they did all this in simulation, of course. To try to do this out on the field would have been very, very expensive and time consuming, of course. And they ran all these analyses and then compared the results. And I'm just showing the main results here. So you can see A and B really did not reduce the pressure drop much. The original side curve warpage percentage compared to CAD was about 32%. So that came down to 30, which is a little bit better. With B, it came down to 28. But with C, D, E, and F, you can see that the pressure drop has reduced significantly, as well as the percentage compared to CAD, the percentage warpage compared to CAD. So they decided to incorporate all these ideas into their optimized design. And they went ahead and ran a trial. So now here's the optimized design and the original design. You can see the deviation of the original curve from what they were trying to make. Here's the deviation of the optimized curve with respect to what they're trying to make, and you can see there's a big delta there. The main thing they wanted to see is what happens when everything comes together. So they went ahead and included those modifications. They made the part, and here the original gap was 2.3 millimeters. They brought that gap down to 0.25 millimeters. So now their assembly was within their tolerance, and they were happy.